We talk a lot about how large language models, LLMs, are trained on these, mountains of data,
Right.
and that gives them their core intelligence, their basic language, their coding skills. But here's the thing.
Mm-hmm.
There's a massive gap between being a smart prediction engine, what some call a great autocompleter, and being a truly helpful, safe, and, pleasant assistant that you actually enjoy interacting with.
Exactly.
So today we're diving into that critical final stage of tuning that takes a smart but often clumsy tool and makes it aligned with us, with humans.
It's the difference between competence and compliance, essentially. You have to teach the model not just what to say, but how to say it, and crucially, what to avoid saying.
Right. And based on the material we're looking at from that Stanford CME295 course,
Mhm.
this development process really follows three distinct stages. Let's quickly recap those for everyone.
Sure. So first you have the really heavy lifting,
Mhm.
pre-training. This is where you train the huge foundational model on just massive swaths of the internet. It teaches the model basic knowledge, code, the statistical structure of language.
Right.
It basically creates that great autocompleter.
A model that's really good at predicting the next word.
Exactly.
Yeah.
Then comes the first major step toward being useful, which is supervised fine-tuning, or SFT.
SFT.
And with SFT, you tune the model for specific tasks. You feed it curated examples like question-answer pairs or instruction-response pairs, and you're training it to follow instructions and act like a functional chat assistant.
And then there's the necessary third step, which is the absolute focus of our deep dive today.
Preference tuning.
Preference tuning. This is where we inject human values, alignment with our preferences on tone, helpfulness, safety. The mission is clear. We need to understand why SFT isn't enough, and then we'll break down the high-stakes methods used to do this, specifically RLHF and some of the newer alternatives like DPO.
Okay, so let's unpack that necessity first.
Yeah, why do we even need a step 3? I mean, if the model has ingested all the world's data and then been fine-tuned on thousands of high-quality examples, why would it still misbehave?
Because SFT is essentially trying to teach the model a function, map prompt X to response Y. But in the real world, especially with open-ended chat, there isn't just one perfect Y, and the model's weights will naturally drift toward what's statistically likely, not necessarily what's desirable.
And the sources gave a perfect, simple illustration of this. If you give an early SFT model the prompt, suggest a new activity I could do with my teddy bear.
An SFT model might give you a cold, unhelpful, or even slightly judgmental response. The source example was something like, I would suggest you to not spend much time with your teddy bear at all.
Ouch. Yeah.
It's technically answering, I guess, but it completely misses the mark on tone, on context, on helpfulness. It fails the human preference test completely.
It certainly kills the fun. So let's get into the technical roots of why SFT alone just isn't enough to capture this essential nuance.
Well, there are two core technical reasons. First, it's just the difficulty of building the SFT dataset itself.
Okay.
To truly train a model that covers every possible useful task and maintains the right tone, you have to compose this vast collection of very high-quality prompt response pairs. And creating those perfect gold standard responses it's just time-consuming and incredibly difficult to scale.
Right. You're asking human labelers to be perfect, comprehensive scriptwriters for every imaginable conversation. That just sounds unsustainable for alignment.
Precisely. And the second big reason is that SFT teaches the model what it should predict. It's all based on positive examples.
Okay.
Preference tuning, on the other hand, is about injecting a negative signal.
Mm-hmm.
We need to teach the model what it should prefer, or maybe more critically, what specific outputs or tones it should not predict.
That distinction is fundamental. It means we stop asking humans to create the perfect answer, and instead we ask them to evaluate the model's own answers.
Yes.
That shift from generation to comparison sounds much, much easier to scale.
It is far more scalable and reliable. It's generally easier for you or me to look at two poems and say A is better than B than it is to sit down and write the perfect poem from a blank page.
Right.
So for LLM tuning, the preferred method is pairwise preference data. For a given prompt, we generate two responses, say output A and output B, and we just ask a human judge to pick which one is better.
How do you make sure those two outputs are different enough to make it a meaningful choice?
Well, we often use the SFT model itself and just crank up its internal temperature setting. A higher temperature encourages more diversity in the output, so you get two answers that are substantively different. Or we can take a bad response we see in user logs and have someone manually rewrite a better version, which creates a very clear bad versus good pair.
And you mentioned that while we could use a really nuanced scale, much better, slightly worse, in practice, it often just defaults to a simple binary. Why avoid that nuance?
Because subjective tasks, like judging tone, they introduce a lot of noise.
Yeah.
One person's slightly better might be another's much better. When you try to capture too many of those gradations, the labeler consistency drops and your data quality suffers. A simple, robust binary scale, better or worse, just provides a cleaner, more reliable signal.
Okay, so once we have this robust data set of millions of these comparisons, A is better than B, X is better than Y, we move into the heavy machinery of training. Let's start with the traditional famous method that pioneered all this, reinforcement learning from human feedback, or RLHF. It's a two-stage process.
Stage one is the crucial step, training the reward model, or RM.
The RM.
The RM is typically a smaller version or a copy of the base LLM, and is trained entirely on this human preference data. Its only job is to take a prompt and a response and then output a single numerical score, a reward score. So it might be, zero point 0.8 for a great answer or -2 for a harmful one.
So it's synthesizing all those millions of binary human comparisons into a single quantifiable metric that the LLM can optimize against later. How does it actually do that transformation?
It uses a probabilistic function, known as the Bradley-Terry formulation. Essentially, the model is trained so that if a human judge preferred response A over B, the RM learns to assign a score to A that is higher than the score for B.
Ah, so it learns the relative difference in quality, and that difference informs the absolute scoring system.
Exactly, and this is a crucial detail. The reward model is trained using pairwise data, but when we use it later, it operates pointwise. You can score any single input-output pair instantly. It becomes our automated human judge.
And just quickly, this is where the term RLLIF comes from, right?
Yes, reinforcement learning from AI feedback. It's the same concept, but the judges generating the preferences are other AI models, not humans.
Got it. Okay, so now the RL part kicks in. Stage 2. Aligning the LLM via reinforcement learning, we have our reliable judge, the frozen RM. The original LLM we want to tune now becomes the agent in this RL environment.
Right. The user prompt is the state. The LLM generates a response, which is the action. And our frozen reward model provides the score, which is the reward. The goal is simple in theory. Just update the LLM's weights to maximize that reward signal.
But this is the stage where developers start tearing their hair out.
It is, because we can't just blindly maximize that reward score.
That sounds like a recipe for disaster.
It is a recipe for disaster.
Okay.
We have to introduce strong constraints. We're trying to maximize the reward while making sure the updated policy, the new LLM weights, do not deviate too far from the SFT base model. If we move too far, we run into two major risks.
Let's talk about those risks because they seem central to why RLHF is so hard. What's the first one?
The first is catastrophic forgetting. The original SFT model holds all this valuable knowledge. Grammar, facts, task capability, everything it learned. If you push the model weights too hard just to become more friendly, you risk wiping out all that foundational knowledge.
So it becomes a highly empathetic moron, basically. It prioritizes tone over truth.
Precisely. The second risk is maybe even more frustrating for developers. Reward hacking. Remember, the reward model is only an imperfect proxy for human preference. It's trained on noisy labels. So if you optimize too aggressively for its score, the LLM will find a loophole.
Right.
It will learn to generate outputs that maximize the metric without actually achieving the real goal.
That's the lecture versus applause example. The real goal is informative content, but the model learns that telling jokes gets a higher immediate reward score from the imperfect RM.
Exactly. It's optimizing for the proxy, the RM score, instead of the true goal, which is human satisfaction. And to manage this complex trade-off, we use a specific powerful RL algorithm called PPO.
Proximal policy optimization. PPO is the workhorse of alignment. So how does it handle this balancing act?
PPO uses a loss function that balances two opposing forces. It tries to maximize the reward, or what's called the advantage, but it simultaneously includes a penalty term.
And this penalty is critical.
It is. It's usually the KL divergence.
That's a mouthful. For listeners who aren't mathematicians, how should we think about KL divergence here?
Think of KL divergence as the leash on the dog. It measures how far one probability distribution, our new LLM, has strayed from a reference distribution, our original SFT model. By building it into the loss function, PPO ensures the new policy doesn't take too large of a step. It keeps the model proximal to its base capabilities.
It's the mechanism that protects against that catastrophic forgetting. It says, get better at rewards, but don't forget how to be smart.
Yes, but the cost of this power is high. Trading PPO is notoriously complex, it involves heavy hyperparameter tuning, and you have to run and manage up to 4 separate models simultaneously.
4 models.
Up to 4. You have the policy, which is the LLM you're updating, a value function model, the reward model, and the frozen base model. That complexity is exactly why the industry started hunting for alternatives.
That sounds computationally expensive and just so difficult to maintain, a multi-stage process prone to instability. It makes perfect sense that researchers would look for simpler, cheaper ways to do this.
Absolutely. Yeah. And one of the first straightforward workarounds, if you already have a trained reward model but want to avoid the RL part, is best of n BON.
I like the simplicity of the name. How does it work?
It just bypasses the RL training entirely. The idea is, for every user query, the system generates n different completions, say 5 or 10 from the SFT model. It then uses your trained reward model to score all of them. So if your scores are 0.8, it gets 2.0, 0.2, and so on. It just returns the response that got the highest score, 0.8.
So we've effectively eliminated the entire messy RL training stage. That's a huge win for development cost. But there's a trade-off.
A significant one, it shifts the entire computational burden onto the inference stage. Instead of querying the model once for a response, you now have to query it n times and then score n times for every single user request. At scale, this just drastically increases latency and operational costs.
So BON is a great research tool, maybe a quick fix, but not a production solution for high-throughput apps. This brings us to the second major alternative, which is gaining enormous popularity, a DPO, direct preference optimization.
DPO is often called a breakthrough because it's a supervised method. It completely eliminates the need to train a separate reward model, and it gets rid of that complex, unstable RL training loop.
Wait, how can it do preference tuning without a reward model? That seems to defy the whole method we just discussed.
This is the elegant mathematical insight. DPO starts with the realization that the optimal policy, the LLM weights we're trying to find, is implicitly related to the optimal reward model. The LLM policy itself, when you formulate it correctly, can act as its own reward function.
So the LLM is both the agent and the judge.
In a sense, yes. DPO derives a single clever loss function that operates directly on the raw human preference pairs, the winning and losing completions, and uses the model's own probabilities to tune itself. It's supervised learning all the way down.
That sounds dramatically simpler and more stable.
It is. You only need 2 models, the policy you're tuning and the frozen base model for that KL constraint. This reduces memory, it speeds up training, and it avoids all the instability of RL. Now, while some benchmarks suggest a perfectly tuned RLHF model might get marginally better peak performance.
The simplicity is a huge advantage.
A huge advantage. The ease of implementation and stability are why DPO is being adopted so rapidly across the industry.
Okay, that clarity really helps cement why DPO is such a popular choice right now. So let's bring this back to the user experience. We started with that unhelpful SFT model being rude about a teddy bear. What's the practical result of all this? Let's use that final example. Asking about washing a toy.
Right, let's take the prompt. Can I put my teddy bear in the washer? The SFT model, which knows facts but not preferences, might give you an abrupt, though correct, answer. No, it might get damaged. Try hand washing instead.
It's technically useful, but it doesn't build any trust or rapport.
Exactly. But the preference-tuned model, the result of this final alignment step, has learned that humans prefer a more empathetic, personalized tone. The response changes to something like, it's better not to, your teddy could get hurt. A gentle hand wash is much safer for special toys.
The underlying facts are the same, but the behavior and tone have been completely aligned.
The knowledge is the same, but the delivery is optimized for human interaction.
And that really is the core takeaway.
It is. The journey of LLM tuning goes well beyond just initial knowledge acquisition. This final step, preference tuning, is where the model is truly refined into a trusted user-facing tool. And the choice between methods is a fundamental trade-off. You can maximize peak performance with the complexity of RLHF, or you can prioritize simplicity and stability, where methods like DPO are now dominating.
And here's the provocative thought that should stick with you. Preference tuning is essential for making these models safe and friendly, but that alignment is defined entirely by the preferences collected from human raters or sometimes other LLMs. And since human preference is inherently subjective, what's friendly in one culture might be condescending in another, we have to recognize that this process is less about finding a universal scientific truth and more about continuously refining a statistical model to capture nuanced, ever-shifting human values. This means the alignment process is never truly finished. It's a constant, iterative pursuit of better proxies for what we find desirable.